transcripts. So we want to have this sample to be aligned or mapped to these transcripts, right? And yeah, and this is just a Python code that will count that how many reads are mapping or aligning to that. You don't need to worry about it. You just need to use it. That's how it looks like, right? Quite, you know, a foreign or alien language, but that is not alien for us because we ourselves, programmers or computer scientists or computational biologists, we are aliens, right? So we know this language. So algorithms are written in the shape of something which is somewhere in between the computing language and somewhere understandable by the human. So that thing is called as pseudo code, but this thing is not a pseudo code. This is actually a code, right? So somewhere in between. Obviously, these are the English. It's written in English, since we are working with the English language. We are the English language speakers, or we understand English here. If we've been doing these things in Chinese, we could have done in Chinese or other languages. But again, a layman doesn't here. So there is another way in between, that's between English and this, the actual code, or the language which are sentences which we speak, or the words which we use in common life. That thing is called as pseudo code. It looks like a code, but at the same time, uh, person can read it. Again, that person should be coming from discipline, because for the layman, still that thing is difficult. So that's the code which we will use for counting these reads, how many reads are aligning to which transcript, right? So here we are using one tool. Now we can see this thing in Linux. The command is head. Head means show me the top few lines of of this file named as mu1.txt. So that contains the read fragments. How many fragments are there? There is a command that we can use called as grep. So if you do grep dash c, c means count, and within quotes you can pick up a character that's only present in your id or read fragment. So that's, for example, this add thing. So that add thing we can count from which file, mu1.txt, right? So it tells us there are 1000 at signs here. So there are 1000 lines that start with at sign. That means 1000 reads are here. We can do that, right? If we just do grep, and rather than dash c means count. If we just do grep, it will simply capture all those lines that start with at sign, and then he is marking these things as red. So he's picking up all those IDs. If your professor wants to, you know, wants you to store the genes or transcript IDs outside in another file, you can do that. But what we're gonna do with the read IDs, maybe we can do the transcript IDs. Maybe we might be interested in getting the transcript IDs. That we can do it, right? I'm sorry. What was that? Grep. Uh, yeah. So what was the name of the file? Grep. That's weird. So again, grep. What was the name of the file? Yeah, 80 transcripts. Sorry. Not this one. We do grep, and then on to this file 80. What was that? 80 underscore transcript. So no, I'm not getting the at sign, but I want to get those greater than signs. So that's my gene ID. So 81G 04480.1 910.1 920.1 930 520 70 90. Right? So these were the genes or the transcripts which are present. How many of them are there? I guess 20 to 25 transcripts are there in this file. It's a small data set that is just there to help you practice. Control L is a duster, so it will uh, clean that board for us. We are using just two commands here. One of them is called as Bowtie, right? So Bowtie2. So Bowtie2 is the tool which we are using. Bowtie2, and then we do build. Bowtie2 build, and the name of the file with which we want to make the indexes. So we need to build the indexes. We covered what are indexes. The file on which you are aligning your target reads, that file should be converted. We just need to make its indexes. So the command is Bowtie build. You can just write Bowtie build and then it will teach you how to run that command. So it says you can run it as like this. So Bowtie2 dash build, and then options may you can write reference in means that file which you want to use as reference. You just let him in the input file name, and this is the name of the output file with which you want to store those references or those indexes of those that of the reference file. What are indexes? We covered that last part, but just to refresh, like for example, you go to a library and there are the books. So we have the records there in on the front desk. You have in our times we have the drawers. We used to pull them, and there were the cards in it, and then we go into the drawer saying A, and then there was the drawer for B and C and D. So A wali books here, B wali here, C wali here, and then we open up, and then again those indexes are placed in a sequence. So the books starting with double A come in front, and then the ones which are starting with A B, about this, about that, they are then the following that. So then we match the second character and third character, and finally we used to pick up the card, and that card has this written information that this book is present in drawer number 13 or 20 or whatever, and we used to give it to the librarian, and he used to then bring that book for us and issue us those books. So that indexing thing is something similar to it has been done here. So your original reference file is one, but it makes six other files or six reference files out of it. So that makes this alignment thing quicker, right? So if you know that your objective lies, there are six rooms in a house, and someone tells you that the thing which you are trying to find is in room number 3, so you can straight away go to room number 3 rather than going into all six rooms. If you're visiting all six rooms, that approach is different. It's called as brute force search. So here we are going with some intelligent thing, right? So that indexing is somewhat you know similar to this, where it can help do this search or this alignment thing quicker, right? So there is a command. He said you should give this command like this. So there is this thing usage Bowtie2 dash build, and options when there are different options. Dash F means reference files are fast stay. That's the default case. Dash C means the reference sequence given on command line. We are not doing command line, we are in Ubuntu. Command line is something which we do in Windows. The DOS command line, we already did some practice a few lectures back, and then the rest of the commands or rest of the options you can explore, but we are not using any one of those options for now. We just keep it simple, right? So we just go with the very simple basic command. So that is just Bowtie2 dash build, right? And then we give the input file name, that is at underscore. If you don't give it, he will make the indexes, still make the indexes. Now he's not doing that, but the previous versions they were doing. So we go up arrow key and repeat the command, and here we just give him the name as at underscore indexes. I can call it as my indexes, you can call it as your indexes or Sadia's indexes or Laiba's indexes, but whichever name you give, it will make their indexes on that name. So to be having on the same page, we just write it as at underscore indexes, and I just do enter. So he's doing something, right? And then when he returns, I do ls and see that six new files with 80 indexes, dot one bt2 means bt2 is the extension telling us that this file is coming from Bowtie2. The previous versions were just Bowtie or Bowtie1, it was bt, and now it is Bowtie2. And then these are AT underscore indexes dot one dot BT2 dot 2 dot 3 dot 4, and then it says AT underscore indexes dot rev dot 1 dot BT2. Rev means reverse indexes. So 4 forward index files and 2 reverse files, because sometimes the genes are not mapped to the forward strands. This sequence which you are actually getting, for instance, this one is all in forward direction, right? This thing which you actually see even in the databases, the sequences which you get in FASTA format, technically they are all in parallel. So what we do is head and AT underscore scripts. Now we get another letter. So this is also a forward file. Okay. Let me see what we have in AT underscore indexes. I just wanted to tell you that ugly machine language and how it looks, binary alignment mapping that files. So that's pretty fun.
From the instrument. The Bowtie2.
Right. So we have those AT indexes, right? And dot, for example, let me pick the first one, dot BT2. So can you see anything? Some weird ugly characters, they are there. So that's that binary file. So that's there in those which we cannot read them. So that index files they are converted into this machine language. So in machine language, computer can compare or map them real quick, right? And again, he is getting this search space is divided into 6 different sections, so that will make it easy and quicker. Right, so we do next is we just want to run the file with where is my command. So I just write this and he can tell me what is the way we can do that before I open up. I'm lazy. So it says usage is Bowtie2 and dash x means the index file. You must write dash x. Previous versions you don't need to do that. And then you need to give him the input file, and then you need to just tell him that this file is short or long. So you just need to add this x thing here. Rest of the options you can simply check, right? So where is my cursor? I can just simply do what I can do over here is enter. So control L. So what is that? So Bowtie2, and then I can write dash x. X means my indexes. What was the name of the indexes? AT underscore I. You just need to remove this dot. Rest of the things is common. If I do like this, AT dot one indexes, so he will simply now I have narrowed down him to only align it to this one out of 6 files of the index files, right? But I want them to align with all of them, right? This one, and then the input file name you want txt, that was the name of the file, and enter. So he's doing the alignment and he's printing the alignment on this console or on this terminal. This thing is called as terminal, and here I can see some of the gene IDs are written or transcript IDs are written. So that means this read, this one ye wala jo hai, that map to this particular transcript. This guy does not map to anyone, 000, and so this is the output file that is printed or written onto my computer. So this guy is for instance mapping here and so on, right? So but I cannot do anything with this output file unless I store it, right? So in order to store that, there is just simple one way of doing that. We can see this file is also that big, so he has taken much of my terminal, so it's really hard to find that. That's why we do this head and tail thing, right? So here so again I do up arrow key, and now I just do right arrow. So that means anything on the left side of this arrow should be stored here, and I can write the file name as mu1 dot out or output file or just output, right, and just enter. So nothing is printed here, but it is stored into a file called as mu1 dot output. I can just simply go here and I see there is these index files which are created in this folder. So everything which we are doing in Linux, since we are having the access to this folder that is in Windows while sitting in Linux, so each file and figure will be stored here in this folder, right? And in a moment, one more command, and then we will back to our Windows, and then we will be doing the rest of the fun with Microsoft Excel and R. That's tomorrow, by the way. Right. So where
Yes,
is that?
sir.
Yes, please.
Sir, why we have created 4 files for forward sequences with Bowtie?
Very good question. Actually, I missed that to explain. Since theoretically we believe that most of the genes are on the forward strand, so some of the genes they expressed on the other strand are reverse strand also, but I guess their numbers are less, so that's why they had, he tries to map a read. Read is also in forward direction. The transcripts are also written in the forward direction in the database or on the NCBI or wherever you get them. So what he does then is first he tries to align them as such, both in forward directions. Then he take the reverse complement of that read. You know how to take the reverse complement of a sequence, right? Anybody? How can we take the reverse complement of a sequence? So for example, so that's my read fragment. So that's in the forward direction. So this is 5 prime, 3, 3, 3, 3, and this is the 3 prime end, right? So we go here, you take this read, it is A, and you now start from here. So that's it's 5, the first one, and then you come back up till this point, right? So this one is first, this one is 100. So here in the reverse strand, this one is first, this one is 100. So this one is the 5 prime end, right? And this one is the 3 prime end. So for the bottom one, it will be 5 prime here, 3 prime here. So what will be the reverse complement of A? So A is converted to T, and then the next A is converted to T, and G is changed to C, and then A to T, and so on. So these are the reverse complements, right? So he will take the reverse complement of this fragment, and he will also take the reverse complements of all those transcripts, and obviously these transcripts they were reverse complemented, and then their index files they were formed. So he will simply take those reads and reverses them and maps them with this rev things or reverse index things, these two files. So and then we can have them, right? And to distinguish which one maps with the reverse versus which one maps with the forward, we can just see here. Here is my output file. So new one dot right. I can just open with more apps. जरा माइक म्यूट कर दें जिनका भी है, right? So nodes. Oh yeah, so that's my output file. So that's my output file, and this so it looks like, and this is the SAM format. It's not BAM format yet. Some of the tools they directly give you the BAM format, but Bowtie is nice, so he wants you to read that output file. So at the top, he is giving you all those transcripts and their lengths. So this transcript 4480 has a length of 648. This has almost 1020. That's almost 1 KB. This is 1.1 KB. Some of them are smaller, 835 bases, 999. Some are longer, some are smaller. So transcripts, their names and their lengths are here. That statistics, and down there, which read is mapping to which transcript. So this is read number 1, and then its sequence, nothing is written here, 000. So that means it's not mapping or matching to anybody. What I can do is I can open up this file with something like Microsoft Excel, right, and just show you in a moment what I'm trying to tell you, that there are some of the reads that will be mapping with the reverse elements are reverse reads. Those reads are also classified into forward reads or reverse reads. So maybe they are coming from the genes which are present on reverse strands. Okay, so some of the reads are coming as forward reads. Most of them we believe are forward reads, but some might be coming as reverse reads. So we go on Excel. So we're gonna do in latest versions of Excel. So you go open and go browse. You go to desktop. Then you have this NGS thing, and this file is not Excel file. I just do all files, and now it will be here. And then once it opens, he just gives you the options. Just do next and then do finish. So he will separate that file. I just allow me to get rid of these things till this point. Delete and now, yeah. So that's the ID thing here, and this is the flag. We call them as flags. We can sort them on flags. So I can go into this file data. Tomorrow I'll teach you Excel, lot many things in Excel, so you'll be excited because some of the things you might have not done before, because we just simply take Excel as something to store our data, but Excel can help you a lot. So I can go from largest to smallest, and 16 is where they are mapping. So these are the genes on which these reads are mapping. So 270.1, for example, what I can do over here is I can go to data, then I can go to sort, and I can add another level. So first I sort them on this thing 16, and then I can sort them on the second column. So over there I can also sort them on the basis of their gene IDs. So this one is 80.1, so that's mapping, and there is one flag here that says plus or minus. So that is the information about whether they are aligning to the plus strand or negative strand. The bottom ones are all zeros, so zero means they are not mapping anywhere. Then this guy, for instance, 10 has three reads on which this ID was found. Three records have this ID in between them at position number 3. So that means these are the three reads which are mapping to this guy. 759 means 759th nucleotide or 759th base and then beyond. That's obviously this read is of size 759. So when it matches to the reference is going from 759 to 858. So that is the place on which this read is mapping. This guy is going from 720 to 819. We'll have one less. Now this guy got three or four of them mapping on this guy, right? And we can do that, and we can check that because we are not doing this quantification or counting thing here. Rest of the flags you can just Google and go to Bowtie2, and it can tell you what the rest of these digits they are indicating. Okay, all right. So last but not the least, Control L. We have 5 minutes. होगी class? दोनों खत्म? वाह जी वाह. चलो जी. Wrap up. अदील आया था. क्यों? पता नहीं वो भी चला गया. अच्छा. Let me finish 5 minutes. So we have here ls, right? And so Python code can then give us the counts of the reads. So Python is the latest version right now on this Bowtie is Python 3, and that code is there is a code written as get counts underscore updated dot py. I just to enter, and he says that use it. You should write dash in and then give the input file name. So which file you want me to count the reads in it. So I can go again up arrow key, and then I can do next is what's the name of that file. So I do dash in. Yes, I just put this thing dash in. In means this input file name, and that input file name was kya naam rakha? One dot output, sorry, output. Now the previous output will become input to this code, so he will just simply go on that and count how many reads are mapping to which genes. So for example, 4270.1 got 9 reads mapping to its, 9910.1 got 7, 7090.1 got 12, and 800.1 got 6. So that is just the counts of the reads mapping to each gene. So now our file becomes numeric, it goes into the numbers, and now we can simply process this into Excel or R or someone else, and then we can do the rest of the analysis. बाकी हिसाब किताब हम फिर Excel में और R में कर लेंगे, because now our data is becoming numeric data, so we get our file in numbers. So we love to play with the numbers, by the way, right? Okay, so up till here I think enough for today. Any questions, queries, concerns, let me know. Any comments, the people who are new to us. We are in the middle of this course. Probably we will have how many weeks? This is our third or fourth week?
Fourth.
So we have 1 week more to go, and then we wrap up this course, and then we start the, are we doing NGS next, or are we doing data analysis?
Data analysis.
So we are going to data analysis and ML and AI thing, and then we'll come back to NGS probably in December, because we have the people in USA, so they requested us to do that in winter breaks. Right, so any questions, concerns, queries, let me know, and I hope you might have enjoyed today's session. Right.
सर प्लीज गेम खेलना सिखा दे इस पे या वैसे ही बता दे हमें कुछ तो लगे ना कि इस पे YouTube खुल सकती है, इस पे गेम्स खुल सकती हैं, कोई मजा तो आए ऐसे ब्लैक एंड व्हाइट लिनक्स जो है सर।
ओहो अल्लाह की बंदी, ये हमने सिर्फ लिनक्स में ना यूबंटू शेल उसका इस्तेमाल किया। जैसे ठहर दो अभी मैं तुम्हारा बंदोबस्त करता हूँ, एक सेकंड।
ये है कौन?
ये है, बिल्कुल बड़ा अच्छा वैलिड सवाल है इनका। अकॉर्डिंग आई थिंक शी थिंक्स के यूबंटू और लिनक्स is all black and white screen. No, we are just using its terminal or shell. But if your system is all on Ubuntu or all on Linux, why don't you just open up your machine? Mac के users बैठे हुए हैं MacBook
नहीं नीचे अपनी वर्क
एक सेकंड। तो अब अपने वर्क स्टेशन पे, जिस पे that Linux thing is fully installed as an operating system that has everything like Windows. So you have something like Microsoft Office, या समथिंग लाइक पावर पॉइंट। ये तो हमने उसका सिर्फ ना ये शेल इस्तेमाल किया है यूबंटू का टू डू दिस कमांड लाइन थिंग, ठीक है। एंड फॉर योर इंफॉर्मेशन दिस थिंग इज आल्सो देयर इन विंडोज आल्सो। ये जो ब्लैक एंड वाइट चीज़ है, इस तरह की एक मिलती जुलती चीज़ विंडोज में भी है। और हाँ, ये इकबाल साहब, ये आपके लिए मैंने
कमांड लाइन आई थिंक यू आर टॉकिंग अबाउट।
फॉर एग्जांपल अगर मैं ये करता जैसे, और फर्ज कीजिए मेरा कोई भाई या बहन जिसने विंडोज़ मतलब वो मैक से या यूबंटू से आया हो, अगर मैं उसको इसके ऊपर ये सारा काम करवा रहा हूँ और वो समझे कि नहीं भाई विंडोज़ बस यही ब्लैक एंड वाइट स्क्रीन है, तो आई थिंक ये गलत बात है। ये विंडोज़ के साथ ज्यादती होगी। हाँ नहीं तो ही नहीं है, अब इतना संगीन वो ना इसको लेके बट एनीवेज ठीक है। तो हमने वी एक्चुअली डिड दिस थिंग, अपने सिर्फ अभी यूबंटू का या लिनक्स का, या यूबंटू इज वन वर्जन, फेडोरा है, रेड हैट है, और पता नहीं बहुत बेशुमार आ गई हैं, राइट। सो दैट इज जस्ट एन ऑपरेटिंग सिस्टम। आपके मोबाइल्स कौन सा ऑपरेटिंग सिस्टम यूज करते हैं, एनीबॉडी?
एंड्रॉइड।
जी एंड्रॉइड के अंदर भी हम टेक्स्ट फाइल्स या इस तरह की कमांड लाइन टाइप चीज़ें हम खोल सकते हैं, राइट। सो एजाज साहब आ रहे हैं, लेकिन हम जा रहे हैं सर, हमारा आज का वक्त पूरा हो गया। Now we'll be on the roads for almost like 1 hour. And my wing lady is sitting on the table. Let me take your picture. Right? ये उठाओ ना, ये पांडे शांडे मांजो ना, एक सेकंड मैं रिकॉर्डिंग बंद करूँ। ये भी वो जो चाय काफियाँ आपने गिराई हुई हैं इधर।
किधर गिराई है?
वो अभी किसने पी है? मैंने पी है।
मैंने नहीं गिराई।
कप है, आपने दूसरे में फेंटा लगाया ना उसका?
नहीं इसी में लगाया।
अच्छा इसी में। गुड।
मेरे पास कॉफी भी।
रिकॉर्डिंग बंद होगी कि नहीं?
I don't know.
स्टॉप रिकॉर्डिंग। ओहो ठीक है जी।